This video is going to look at the Diels-Alder reaction. The most important reaction in chapter 15 is called the Diels-Alder reaction. It involves taking conjugated dienes and alkenes and adding them together to form a cycloaddition product, which means you're forming a ring. We'll start by adding a conjugated diene in the simplest form, similar to what we saw in the last video, and adding lots of different types of alkenes that are possible, and so we call this piece a dienophile. And we've used terms like this with electrophile and nucleophile before, and so this is the diene-loving molecule. As a result, carbons 1 and 4 of my diene are going to make new carbon-carbon bonds to our dienophile. This means that each of those carbons is going to lose the double bond that's starting there. As a result, the new pi bond is going to be formed between carbons 2 and carbon 3. Just to get some practice, go ahead and start by drawing your simplest product here. Pause the video now. We can definitely get more complex by adding groups to our diene or our dienophile, but here we would have our two carbons come in, again making a six-membered ring, and seeing that our two groups are going to be pointed in the same direction. We'll talk more about the stereochemistry in a little bit. Before worrying about stereochemistry, let's focus on the mechanism. This is a concerted cyclic reaction, and you can actually draw arrows two different ways, as long as you draw them all clockwise or all counterclockwise. So how we can start, if we wanted to draw them clockwise, we can have this double bond come down, push the electrons from the double bond up. That means that those electrons in the pi bond have to go out and make a new bond. You can also draw them counterclockwise, where our double bond goes out and grabs the top carbon, pushes that double bond down, and that means these pi electrons go out and make a new bond to this carbon here. So either way, whichever one is easier for you to see, but we're going to have three arrows drawn together in this mechanism. This is a very diverse reaction involving lots of different types of dienes and dienophiles. Go ahead and get practice drawing the products for these reactions. Pause the video now. We can continue to use our mechanism arrows to help see what's happening, so we can add our three arrows here. As a result, we're going to have a six-membered ring. In this case, one of our pi bonds is still going to stay behind, so we'll have a pi bond on both sides here. And we don't have to worry about stereochemistry because those groups are located on the alkene. For the bottom one, we can do our arrows again, drawing out, starting from my dienophile. And so as a result of this, we're going to have a bicyclic product, and you'll start to see pictures looking in both two-dimensional and three-dimensional for this product. I think the colors really help here, so you can still see our pink five-membered ring that we started out with. Notice the double bond is moved. And then you're adding the two carbons from our dienophile. So we have a new six-membered ring with the two new carbons, while we still have our five-membered original ring that we started with. So because of the diversity of both pieces here, you can end up with bicyclic products. When we're thinking about finding a good conjugated diene, here's where our conformation comes into play. If you have a conjugated diene that is locked in its S-trans form, these are going to be unreactive. Alternatively, if you have an S-cis conformation, shown here, these are ones that are going to make the reaction go much faster. If you aren't locked in one or the other, you can use the free rotation that we talked about in the last video to help draw our S-trans conformation into our S-cis conformation. Notice here, as we swing it inside, my H is still going to be pointing down and my CH3 is still going to be pointing up. Once we're in our S-cis conformation, we can add our dienophile in order to complete our six-membered ring. Notice the equilibrium here going from S-trans to S-cis. This is not favorable, but it still happens a little bit of the time, so we can use these for our Diels-Alder reactions. Now let's focus on the stereochemistry. As we add these together, because it's a concerted reaction, we're going to see syn addition of the diene to the dienophile, which means that our stereochemistry of my alkenes is going to be retained. So for this top one, we're going to end up having our 6-membered ring, and we're going to see that because it's a cis alkene, my two groups are going to stay as cis when I make my cyclic product. Pause the video now and try to draw the product that we would make if we used a transalkene. So just like we kept our group cis when we started with a cis alkene, if we have a transalkene, those groups are going to be trans to each other. So we would have a racemic mixture depending on whether or not my diene came from the top or bottom, but the relationship of my double bond is going to be retained. Where my two groups were trans, they're going to stay trans in my product. What about the stereochemistry of our diene? Here I've given you a generic template looking at what types of substituents we could have on our carbons 1 and 4. These will be the carbons that end up getting new bonds in our 6-membered ring. Here showing the ones pointing directly up and down as our outer substituents, while our slanted ones are going to be our inner substituents. Just like the stereochemistry involved with our dienophile, when we do this cyclization, we're going to see that our two groups that we're pointing in opposite directions are going to be the ones that stay cis to each other. So we would have our outer substituents being cis, and we'd have our inner substituents being cis to each other. The stereochemistry gets more complicated as we add complexity to our dienes and our dienophiles. So we've already talked about our outer and inner groups coming together, and I'd encourage you to use those as a way to help keep track of what's going to happen to any new stereocenters we create at the edge of our 6-membered rings. So again, notice here that our outer substituents are cis and our inner substituents are cis. We have two different possibilities. We can have the H's being shown here going cis to my inner groups, or we can have them going cis to our outer groups. The names we use for these are exo and endo. So in order to keep track of these, I'd encourage you to look at our outer substituent and decide whether or not the stereochemistry of my new stereocenter is going to be cis or trans to those outer groups. If it's the endo product, the alkene substituents are going to be cis to the outer diene substituent, our R0, in this case the methyl group. If it's exo, those alkene substituents are going to be trans. So in order to test to see if you can use this template, here are a diene and a dienophile. Draw both our exo and endo products, correctly identifying which one's exo and which one's endo. Pause the video now. I would start by drawing my 6-membered rings and with my outer group cis to each other and my inner group cis to each other. Then depending on which product I wanted to draw first, that's how I would show my R groups. So here I'm looking for my endo product because my R groups are cis to my outer diene substituents. If an exo product, I'm going to see those being trans to my outer diene substituents. Generally, the endo product forms faster, but for the most part, you're going to be asked to provide both products labeled correctly. Here are 2 questions to practice on. Pause the video now and try to complete these on your own. So again, for the top one, I'd start by drawing my 6-membered ring, and then for endo, I'm going to want to see those groups being cis to my methyl groups, my outer substituents here. I would also have the exo product where those would be trans to my methyl groups. For the bottom part, remember, start to break this into your two pieces. We'd want to see that here is my new bond and here is my new bond. I also see that I have a alkene still remaining on my right-hand side, which means that I have an alkyne to start with. I also see that I have my methoxy groups pointed in opposite directions. So for my diene, one of them is going to be pointed as an inner substituent, one's going to be pointed outer. It doesn't matter which one's which. And then for my dienophile, I'm going to have an alkyne with my ester. That wraps up this video.